Hello everyone, my name is Junfeng Cheng, and I'm from Imperial College London. Today I am going to present our work titled FARS, Gradient Field-Based Auto-Regressive Sampling for 3D Part Grouping. Our paper proposes a new task named 3D Part Grouping. Suppose there is a mixed set containing scattered parts of various shapes. This task requires algorithms to find out every possible combination among all the parts. Assuming we have a set which contains mixed parts from n shapes. Our goal in this task is to use a grouping algorithm to separate these mixed parts and group them by their respective shapes. Our contributions are listed as follows. First, we introduce a novel setting termed 3D part grouping, which necessitates algorithms to identify all possible combinations of the input. Our framework addresses two primary challenges in this task. The first challenge is understanding the relationships among parts, and the second challenge is handling the uncertainty of the potential group's quantities. Finally, we establish benchmarks for our introduced task and showcase the effectiveness of our framework in the 3D part grouping domain. In this figure, we introduce our framework. First, we obtain the per part feature by using a point net to encode all the input parts Pn at the iteration n. Then we use the gradient field-based selection GN to sample a selection vector Cn to obtain part group n, and use Cn to get the rest parts Pn plus 1. Pn plus 1 will be the next input parts at the next iteration. The auto-regressive sampling stops when Pn plus 1 is empty or n reaches the maximum iteration. We here apply random mixing method to create our data sets. We randomly select n shapes from the Partnet data sets. We then mix all the parts into a single set. The sequence of parts are shuffled. We here demonstrate the quantitative comparisons in this figure. To intuitively show our performance of the grouping results, we rotate and translate the parts in all the groups with their ground truth poses after the grouping procedure. Please note that the rotation and the translation are only used for demonstration purposes. We do not use the ground truth poses information in the grouping procedure or the training procedure. The figure shows that our method is able to group most of the mixed part sets, which further demonstrates the strong ability of our framework. However, the other baselines hardly manage to predict the correct groups accurately. We present the quantitative comparisons in the table here. We use precision, recall, and F1 score to test the performance. Overall, our framework outperforms other baselines by a large margin on all data sets. This proves the effectiveness of our proposed framework. We present application studies for our framework here. The table on the left side demonstrates the effectiveness of gradient field learning and graph neural networks. The table on the right side proves the PC sampler outperforms the EM sampler. The best sampling step for PC is 500. We surprisingly find that our algorithm is able to achieve application of noisy part removal in a zero-shot manner. We demonstrate this application in the figure here. Assume you have a set of parts which belongs to a chair. However, you carelessly mix some noisy parts into this set, and you want to remove these parts. Our framework can achieve your goal. The framework can directly output the correct selection for the parts of your chair. Thank you for watching.